Okay, everybody. Testing sound from Arduino's office right now. This is David Quartier transmitting live. I'm gonna turn on the camera. Woo, here I am. Woo, happy Easter, everybody. Today's the day before Easter. People are already traveling around, so this is the reason why this week we're gonna start our program, or we're gonna transmit our program one day earlier than every other week. I have the feeling that I have a lot of echo in my transmission today. That's what at least I hear in my headphones. And since I have no technician, because the guy that typically is with me happens to be sick today, I'm gonna need all of your help to configure the sound on my side. So first of all, the question is whether you hear me or don't hear me. And after that, the other question is whether you hear echo or don't hear echo. So to those of you connected, can you hear me? First thing, or is it too silent? And in the meanwhile, you can also answer the question whether there is a lot of echo or not. Oh, happy Easter from Greece. Hey, Billy from Greece. Really happy to see you there. Does it sound okay? Okay, since people in Greece hear me okay, we're gonna go live. So, welcome to Arduino's LiveCast number 3. Hopefully we'll continue to transmit forever. But okay, as you know, I'm just experimenting with the technology here, trying to learn about how everything works and trying to make it a little bit better week after week. So we consider ourselves in beta state. How will I make a beta state? Something like this. It's like a German beta somehow. Okay, anyway, thank you everybody for being here today. And what we're gonna do today is a special program. As you know, I'm typically doing education livecasts, but people that are coming on the chat, they keep on asking questions whether I can show something a bit more technical at some point. So I think, or I figure out I'm gonna make one of every third or fourth livecast a bit more technical, where I will look at data sheets and stuff like this, just to satisfy your nerdiness. So today I want to start with a question that we got on the Arduino support email list, because people, yes, we have a support email list for those of you that have original Arduino boards. And we got this very interesting question, and allow me to open it on my computer. You can see my screen for two reasons. First of all, is because I don't hook up my computer to the transmission, and the second reason is that I don't want you to see who posted this. It's for privacy reasons. But a user of Arduino's support services sent this very interesting question, and if you're listening to me, you know who you are, and take no offense. We took it seriously, even though we're making a bit of a fun kind of thing out of it, but we took it seriously. So the question is, hello, I was using my Arduino Uno to test material close to the sea. I understand close to the water, and it fell in the water. Obviously the water is salted. It wasn't black when it fell in the water. That's a plus for you. So there shouldn't be any current going in the Arduino at this time, except the condensators, or the condensers, it says here. It should be okay. So I unplug everything and rinse in the warm and fresh water for about 20 minutes. Now that I tried, I can see white oxidation on metal parts of the Arduino. How could I clean it properly? Thanks for your help. Well, if you've ever had any kind of electronics that got wet, you know, who hasn't got his mobile phone into a complicated location and getting all wet, or who doesn't have a cat that has poured a glass of water on the keyboard, or when you were talking to a friend at the university, you pour a glass of coffee on a keyboard, and you know that things happen. Typically you can rescue most of your electronics if you handle them carefully. What tends to break almost every time is the power systems for your electronics. So for example, one of our colleagues here got a cat to pour a glass of water on the keyboard, and the batteries got busted, but the computer still worked after drying it carefully. Another friend had a glass of hot cocoa falling on top of her laptop, and after cleaning it very carefully, it still worked, and so on. So if your Arduino fell in the water and you dried it properly, actually you don't need to rinse it, but rinsing is good, then it should work. So what I did this morning, just to prove my point, is that I got an Arduino board and I brought it out in the sea, and I threw it into the water. So here you see me preparing it, and well, I tied up the board to some kind of weight, and then again to another rope, and then I just put the board in the water. You're gonna see this in a second. Oh. So you see it's a bit of a cumbersome process, takes some time, and then I bring the board down in the water. There you have it. So this was filmed this morning because I wanted to show this live on today's transmission. And well, you will wonder what happened to that board. Well, after taking it back in, it was really cold outside. I washed it, I rinsed it as the question we got from the user, and I let it dry throughout the day. And so this is how it looks like. So let me just turn on some more lights in the room, and yeah, here you go. So this is my Arduino board. This is the weight that I attached to it this morning, and this is the paper that I just used for it not to make anything wet. And as you can see, the board, it looks, at first sight, it looks okay, and it didn't get any further damage. So the first thing is that the board didn't get any of those marks that our other friend commented in his email. This could be provoked because of a longer exposure to the seawater, maybe because the Baltic out here is not very salty in the winter time. That could also be a reason. Regardless, if the board dried properly and there is no short circuits between the connections, there should be no problem. But if you had some sort of like white stuff around the connections and you want to get rid of it, typically a little bit of alcohol, which you can apply with paper or cotton or something, might clean your circuit. There is flux as well as some other materials that are typically used in electronics, but if you don't have the classic stuff, you can use alcohol, which is what we use home every time we want to clean up electronics. So I'm going to just connect the board here. I have so many buttons to press. Woo. So I will connect the board here to my computer and hope it will not catch fire. So here you go, plug it in. The board seems to be working fine. So I now will open the Arduino IDE and I will make a new sketch. And I'm gonna try the classic blink sketch. So I just like say that pin 13 is gonna be an output. And I will just do here digital write 13 high. For those of you that are connecting right now, I'm just checking that a board that I threw into the water this morning is still running properly. I will make it wait for a second, and I will just copy these two lines, and then I will turn the light on the board off. I will make sure that this board is on the right port, COM5, Arduino Uno, and I send the code to the board. I don't need to save it. Here you can see the board, and you see that now, hopefully, the Blink program will start. It's still compiling. have to say. The computer I have for live casting is not the fastest. That's one of the points of improvement that I have here. So it's still compiling, as you can see here. While I wait for it to end compiling, I will say that basically this board was in the water for about 5 minutes, and then I had rinsing for another 10 minutes in the kitchen sink. So now it's done uploading, and as you see in the camera, the light is blinking normally. So see, since the board seems to be working fine, I'm going to be using it today for all of my experiments, if you don't mind. So when I announced the podcast, I said, or the LiveCast, sorry, I said I was going to be working with sensors today. And there is a lot of sensors one can choose. And I looked through my boxes and thought, okay, which kind of sensors do I have available that can be interesting to use? And I thought temperature sensors. Temperature sensors, there is a whole lot of them. And so I brought a bunch of them that I want to show you. So let me just quickly move the board with a heavy weight from the view and the paper that I used to protect it. And I'm going to show you a bunch of sensors that I got from the boxes that we have around. So the first sensor I'm going to show you is this one. It's very tiny, huh? It's also very inexpensive. This is a temperature sensor that is used to measure temperature changes using a resistor network. So this is actually a resistor that changes temperature, so changes resistance with the temperature. So when you apply heat or you cool it down, it changes temperature. And if you build a resistor network, apply power and ground, it will work. I will explain later this more in detail. I will just present all of the participants in today's contest. So we have another one, which is the LM35. You will see here. By the way, I bought this at the local reseller, Electrokit, a friend of ours. But here you see, this is LM35. I will write it down for you later. But this is a silicon-based temperature sensor. It's extremely cool. It gives you temperature in Celsius degrees with a really high accuracy without having to do very much. And I will show you where to find information about this on the internet. Then we have a 1-bit temperature sensor. It's controlled through a 1-bit port, and it allows you to have a whole bunch of different sensors hanging from different pins in Arduino. Some people have used this to monitor their whole house with a single Arduino board and a really long cable. So this is the DS18B20, the next contestant for the list. Then we have these very nice temperature and humidity sensors, the Dht11 that many people are using for their agriculture projects. So this is also a very nice sensor. We'll see it later. It comes in a small plastic housing. And finally, at last, this one has like no information. This is a waterproof sensor. I think this is basically a plastic housing for a sensor that is compatible with the DS18. But we'll check it out. We'll make a program and check whether it works or doesn't work. So today's program will hopefully last for about 40 minutes, and I will be checking out different temperature sensors and answering any kind of questions you guys might have. Okay, so let's go. I'm gonna start with the our friend, the resistant sensor. And I found this sensor in a box that I have had for quite some time, so I have no idea about the characteristics of the sensor, a data sheet or anything like that. What I did in order to cover for that is that I brought with me resistors, like 10K resistors, 100K resistors, 1K resistor, and a very shy and tiny 100 ohms resistor. So what I'm going to do is to build, I'm going to build a small circuit on a breadboard that will be using the sensor and a resistor, and plug it to Arduino and see which is the resistor that gives me the best conversion factor. So just to get you the idea, what this is doing is the following, or what I'm going to be doing is the following. I'm going to make a drawing to explain the idea. So there is the Arduino board, and there is a breadboard. So I will put my temperature sensor here. I will power it up to 5 volts. I will put a resistor. I'm going to paint the resistor in a different color because the resistor, I will be changing it. I will plug this one to 0 volts. And finally, I will add an input to A0. So I will get the information from the sensor and send it back to my computer and show the number on the screen. Okay, so this is the basic idea of what I'm going to be doing during the next 5 minutes, more or less. So I'm having a whole bunch of different things on the other table. So here's the breadboard. And first thing, I get my sensor and I plug it in real quick. There you go. I'm going to take first the 100 ohms resistor. And as I said, this might or might not work. I might have to be changing the resistor a couple of times, so I'm going to put it here at the bottom in this part of the breadboard so I can easily extract it and try with a different one. Then I'm going to need a ground cable. I'll take this black cable as for ground. I will need a cable for 5 volts. I'm going to take this orange cable for 5 volts. There you go. And I will need a yellow cable. Oh, it doesn't need to be yellow, but I will take a yellow cable for the signal that will connect to A0. There you go. And it's in. So then we have the Arduino board with its heavy weight. I have the Arduino board here. I plug in the ground signal, the 5 volts, and finally A0. Here we go. I plug it to the computer, and then I will just take one of the examples from the Arduino IDE that takes the signal from the analog pin and prints it on the serial port. So I can take analog in out serial. This example is one of the classic examples of the Arduino IDE that has it makes use of the serial port, and it reads the information from an analog pin. Analog pin is configured to be A0, and well, it's trying to turn on a light. I will eliminate everything that is not needed, just not to confuse people. And like this. So we just print out the sensor information to the screen, and every 2 milliseconds it will make a new reading and send it back to the screen. As you know, when I read a value, it will be a number between 0 and 1023. And what I want to see is which is the range I get depending on the resistor I put connected to the sensor in this case. So I upload this to the board, and very quickly you're going to see that some of the resistors are going to give us a better range for the sensor, while some others are going to give us a much worse range. So once the information is uploaded to the board, if I open the serial port, you see here that it's giving me a reading, and it's really hard to read. That is 787878. So it's really hard to read on the transmission. I'm going to make the delay a lot slower, so about 50 times lower. So we'll make only 10 readings per second. And in this way, it will be a lot easier to read what we're getting from the serial port. Here you go. And you see now the numbers there. And if I touch the resistor, you see that the number goes slightly up to 10, 11, 12. When I let it go, will slowly cool down. I will blow on it. Okay, and now after blowing on it, you see that the temperature is back to be 7.8. So I will just take a note of this, just to remember. So with 100 ohms, my readings go from 7 to 12. So it's not a very rich reading. The room here probably will have 20 something degrees. When I touch it, the temperature should rise up to like 30, 32 degrees more or less. It's always a little bit less than the 36 that we should be at, especially because I have no fever today. But for that difference of 10 degrees, I only get between 7 and 12. So it's not a really good reading. So I'm just going to change, the resistor from 110 ohms, so from 100 ohms to a 1K resistor. And let's see what happens in the readings now. So here you see the readings by default. For a 1K resistor, which is 10 times bigger, I'm getting 86. And when I heat it up with my hand, it rises up to 100, 117, 118, 100. So 117. So I just took note of it, and if you look at the numbers, there seems to be a relationship. This is 10 times bigger, so you see the numbers is somehow related, but this range is a lot bigger. Instead of having 5 numbers difference, I have over 30 difference, which is giving me a lot more richness to play around with stuff. So let's see if I take the 1K out and I put a 10 kilo ohms resistor instead, which is again 10 times bigger. Okay, and here we go. So right now, we have changed the resistor. You see it's a different one. Right now by default I get 500, so I will take a note of this. With 10K I get 500 by default, and I'm gonna heat it up now, and when I heat it up, the value keeps on increasing, and it goes up to like 590 more or less. So now for a difference of 10 degrees, I get 90 values. That is a lot richer, so I can do a lot of stuff. So as you see, for this particular sensor, given the conditions of the environment I'm in, it seems to be making sense to use a 10 kilo ohms resistor instead of using a 1 kilo ohm resistor, because of the richness I get from the values, which means I can play with decimals in the temperature if I want to. But if instead of measuring the temperature in this room, I was trying to measure the temperature between the room and outside, which is at -1 degree right now, as you saw in the video I showed earlier, the difference might be too big to be represented with a with 10 kilo ohms resistor. I might need to go down to 1 kilo ohm and use that range, because it's going to be a lot wider. So as you see, you need to be playing with this depending on the circumstances. And while these kind of sensors here, from the ones mounted right now, they are very, very cheap. They are super inexpensive. They cost the same as a resistor. They are not as accurate for many cases. So you're going to be interested in using other sensors that are going to be giving you a lot better response. So the next sensor we're going to see in level of complexity is one of my favorite ones to use in projects, which is basically the one that I mentioned earlier, the LM35 that I have here in my hand. Well, I actually have 10 of them. So let me just give me a second to clean up my breadboard. And then the first thing I will do will be to download the datasheet for the sensor we're going to be checking, and we will see how to mount it and how to use it. So take out the paper I used to make the first explanation, and we move on. So let me just look for the datasheet for the LM35, and here, so LM35, and it's a temperature sensor. This is in these images you can see how it works. It has 3 pins. It works between 4 and 20 degrees. That's super convenient because sometimes you might have a project that is powered up at 12 volts and then the sensor is still usable. It has a single output pin that doesn't require any signal conditioning, so you can just plug it directly to an analog pin in Arduino, and the last pin is obviously ground. So the question is, how does it work, what it does, right? Before hooking it up, we can take a look at the datasheet. So this is the original design from Texas Instruments here. This is the datasheet for the sensor, and let me see if I can make it slightly bigger so you can see it big, a bit better. Yeah, here you go. So it's directly calibrated in Celsius degrees, as it says here. It's very convenient. If you're interested in Fahrenheit degrees, there is other sensors that can calibrate in Fahrenheit degrees. It gives you 10 millivolts for grade centigrade, which means that it has an ensured accuracy of 0.5 degrees, given that you're going to be at kind of like room temperature right now. But it works from -55 to 150 degrees. So this is very relevant because it means that in a place like Sweden, this sensor can be used in the full range for measuring outside to measuring boiling water. Because temperatures, they typically don't go under -55. I'm having a problem because I need to open the bag, and I realized that this room has been so nicely cleaned that they didn't leave me any tools. So I'm gonna see if I can do it with the classic key trick. There you go. So I'm gonna take one of these sensors so you see how they look like, because they are really, really tiny. They're like a transistor. So you see, oh, is my hair in the way? You can see it's very, very small. And they are extremely linear, which means you can trust them to see how they work. So you plug them directly to a microcontroller, and the question here is, how do you translate what this gives you into a temperature number? Because this sensor actually gives you a voltage, and the voltage translates into temperature. So instead of like sitting here looking at the data sheet, because otherwise the problem will last forever, we're gonna look online for how to connect it to Arduino, because there is examples of code that you can use to make it work. So in the Arduino playground, for example, there is this old example that tells you that you can calculate the temperature by making this very simple operation: multiply, or let me just make it bigger for you, multiply the reading times 100 times 5 and divided by 1024. And it says here, well, it's a very simple rule of thumb, it's a very simple equation, but does not give you higher resolution temperature changes, which you could do. So in order to do that, you need to do some other operations. So we're gonna first just make the simple example, because this one is good enough for what we're doing in this room. So you need to just plug the sensor to a breadboard, and let's take a look at the pins once more. Here you go. So it has 3 pins. The pin on the right hand side is supposed to be ground, so pin number 3 is ground, so we'll use the black cable for that. The one on the left hand side is power, so we'll use the orange one, and the center one is a signal, so we'll use the yellow cable that I used in my previous experiment. So here you see, they are not the nicest cables, but they do the job. Here I come back with the board that I threw in the water. I think this is going to be a really funny video. And I plug in power, ground, and signal to analog 0. Okay? And I can plug in the board. So remember how it looks like, because we don't need to be going back and forth too much to see how this works. We copy the code that gives us the temperature measurement here. We go to the example here, and we need a temperature variable. It shouldn't be an integer, it should be a float, because we're going to be dividing the number by different values. So first we get the reading, which is sensor value, then we are going to use the code we got from the internet, which instead of analog read temperature pin, this is actually sensor value, which is the reading we made. And the thing we need to print is the temperature variable, which is called temp. There you go. So now we'll be printing out the temperature value instead of that, so directly in degrees centigrade instead of just the number that we saw earlier. So this is a big difference between the previous example and this one, which is that we're going to see real temperature values. So you see here 21 degrees more or less in the room, and I'm going to heat it up with my hand, and you see how the temperature rises, 26, 27 degrees, so probably I might be a zombie because the temperature is not becoming too big. And I will try to just throw some hot air on it. And you see, basically that's how it goes. So as I'm showing this, Billy from Greece is commenting here that the LM35 is noisy. We're using long wires. So I wonder, Billy, if you think that the wires I'm using here are long or short, because they are about less than 10 centimeters long. Anyway, he says, he gives the advice that probably you should, people take into account. I will just open here the channel. So if you use long wires, it's noisy. He's using a 1 kilo ohm resistor from the output and then a 10 microfarads capacitor. So basically this is making a low pass filter. This is what Bill is doing to ensure that the signal, the analog signal that comes from the sensor, is not bumping back and forth, but it's filtered out. So thanks, Billy, for the tip. So you know, I will actually make a quick drawing of what he mentioned. So you have the sensor like this. This one goes to ground. This one goes to 5 volts. And from this one, Billy suggests to use a resistor, 1 kilo ohm, and a capacitor like this. And this goes to the digital pin. And this one is 10 microfarads. So what happens when you have something like this is that if the signal here bumps for whatever reason, here it gets filtered out. This is what we call a low pass filter, made with a resistor and a capacitor, and cleans up the signal. So thanks, Billy, for the tip. And as you see, I'm really open for any kind of tips. It's not like I know everything, thanks God. Otherwise, I wouldn't be here. So now we saw 2 different sensors. We saw our noisy friend, very slow reacting, resistor-based temperature sensor, and then we saw the LM35, which is a silicon-based temperature sensor that is here, that is very easy to use for projects. Like if you have to make a project with students, this is like super useful for doing simple data logging. What I would do if I was making a project with students, I would probably discard the decimal numbers if I was, for example, measuring room temperature, and I will only use it for other values, or eventually, as Billy mentioned, I will establish a filter. I will build a filter for that. So let's go to the next one. This is going to be an interesting one. So this is the DS18, and so DS18 is a very interesting sensor that uses a one-wire communication protocol. And I remember that somebody made a very interesting project where he used like 100 of these sensors to monitor his whole house. That was interesting. So where can we find more information about this one? Well, let's go on the internet again, and so we go to the DS18 DS18B20 is the name of it. And here you see this is basic information about the sensor. It has ground, signal, and power. If you look at it, it's the actual opposite polarity than the one that you saw. So it's very important that that you check this out. So even if some sensors have the same package, this is called the TO92 package, they might have a different order in the pins, how they're set up. So it's very important that you check out and when you teach somebody else, you remind them that the packaging doesn't mean that the pin order is the same. So this is not saying as much, except for the fact that it's the way you connect it. So let's look for some other information. So this was the DS18B20. Make a search on all, and you see waterproof DS sensor, part number Maxim. So this is a sensor from Maxim. Let's just zoom in so you can see it better. So this is a digital thermometer, so it's different from the previous two ones that we saw because they were analog thermometers, and this provides either a 9-bit or a 12-bit Celsius temperature measurement, and has an alarm function with non-volatile using programming upper and lower trigger points, which means you can use it to detect that the temperature goes over or lower a certain temperature value. It's communicating over one wire bus, which means you can use just one cable to communicate to it, and it could eventually take the power from the data line. So you could hang up a lot of these ones just on two different wires, one for ground and one from power plus signal. We're not going to see that today here. It's a bit complicated to explain, but it is perfectly doable. And it says here, this is the key aspect. Each DS18B20 has a unique 64-bit serial code. So this means that you can have a lot of these sensors hanging from a single pin on your Arduino board. So this is the interesting aspect. When we look at the ranges, it's a bit better on the lower range than the previous sensor. It goes from -55, but not as good. It goes up to 125, so it's a bit worse than the previous sensor we saw. The accuracy is the same. It's 0.5 centigrade degrees, and it requires no external components. Okay, so this is not going to tell us a lot about how to hook up the sensor to Arduino. Somebody has taken the time to do that for us, so we're going to just search for a library to do this. So DS18B20 Arduino, and here you see, oh, we have it on the Arduino Create platform. So let's take a look at this one, and Arduino thermometer with DS18B20. Oh, funny enough, this one that you see here is exactly like the one that I have without any naming, so probably both are going to be the same. So Konstantin Dimitrov has made this project a couple of years ago on the Arduino platform using Arduino Uno, this chip, a resistor, and some jumper wires. So let's take a look at how it's done. Here's information about the sensor. You might recognize this picture here, where you can see it's just showing us the pinouts of the sensor, and we're interested in how it's connected. Let's go down. It's using the one-wire library, so we need to install this library, and this is the way you hook it up. So it's having the signal pin that is pulling up the signal, as you see here, to 5 volts, and it's using pin number 2. And here's an example of code that using the one-wire library is going to be sending the data back. Okay, so the question is where we can find this one-wire library. So and the library that is needed for the Dallas temperature sensor. I have no idea because I haven't tried this before coming in today. So I'm going to check whether these libraries exist in the Arduino IDE library management system. So I will just go to Sketch, Include Library, Manage Libraries, and we're going to search here for one wire and see whether the one wire library exists. One wire, and oh, look at this. Dallas temperature library. This one is made by Adafruit, and this one is for the Max 31, so it's not the one we want. There's the Max library here for the same one wire, access one wire temperature sensors, memory, and other chips. And one wire hub, one wire slave device emulator with support of 32 simultaneous one wire devices. So I just see there is quite a lot of stuff. So I suspect that this one wire hub allows you to emulate any kind of these devices with an Arduino. So make an Arduino become a one wire slave object. So your Arduino could become one of these. So you could use it in a larger network to send information. But I suspect this is one wire library by Jim Studd, Tom Pollard, Robin James, well, all of these people building it up. Is the one we need. We will install the latest version. There you go. And let's see what else we need according to the website. Dallas temperature, it does all of the calculations and stuff. So let's see whether we can find Dallas temperature. There you have it, by Miles Barton, Tim Newsom, Gil Barros, and Rob Tillard. Rob Tillard, by the way, hello to you, one of our moderators in the Arduino forum that's been doing a tremendous job over the years, so big kudos to you. And so this is the sensor we're going to try out, and it's for the DS18B20. So this library covers this sensor, so let's install it. And so now we have both libraries installed. So the next thing I will do is to mount the circuit. Let's remove this one so that people don't get confused. This is the exact opposite than what we need. I will unplug everything just to start from scratch. I keep on playing with this board just for the fun. I hope nobody will think I'm too crazy. And so we have our sensor. If you remember the information about how the sensor has to be hooked up, here's the pinouts. And farther down in this example that we're using is also you consider that there is a need to make a pull-up. So I will first plug the sensor on a board. Oops, I very cleverly plugged it wrong. There you go. Then plug the ground cable. The signal cable is in the center once more. And the power cable is at the other end. And the important thing here, remember, is that we need a pull-up resistor according to the circuit. And I'm going to take a 10 kilo ohms resistor. Even though here he's using a 4.7K, I'm hoping that it will work fine with this one that I'm going to put. If it fails, I will probably have to change it. So I'm going to be very creative with the circuit. I don't like to make it this crowded, but I'm just trying to make it very quickly for the show. Okay, so we plug in ground and power, and signal is going to be number 2 in this example. I'm just going to fetch whatever example is in the library, so I'm not really sure I will end up with the same connections. You see, I'm just plugging in the board. So the sensor is here. It's a bit hard to access. There's the connections, and I go back to the Arduino IDE. In the Arduino IDE, I'm going to check the examples from the libraries he has installed. So there should be examples for Dallas temperature. This is great. And there's examples for 2-pin DS18B20. I don't think this one we're using. But I don't know. Let's open it up. So in this example from Rob, once again it's Rob, we have here the one wire library. It's included, the last temperature is included. It's saying one wire bus 1 is in number 2, one wire bus 2 is in number 4, and the last temperature control library demo 2-pin DS18B20. So this example, what it's doing is using 2 sensors, and they are one inside the house and one outside the house. That's why they're called one wire in, one wire out. This is why I read it. And so it's going to be showing temperature from 2 different sensors. I could wire up a second sensor because I do have a second sensor. What I'm going to do instead is to clean up the example so that I will just make it for one single sensor instead. So there you go. So pin number 2, one wire that declares here the in-house sensor to be there. Yeah, I don't need to put 2 wires here, and we instantiate only the in-house sensor, and we begin the communication to it, requesting the temperature. Once it's done, prints out the temperature in-house. There you go. So this is the example. I'm gonna add the delay because I don't know how this example works. It might have a delay because of the communication with the sensor itself, but I just don't want to install the serial port because of not taking care of this. Just summarizing, this takes a one wire library, this takes the Dallas temperature sensor library, defines that we're going to be using pin number 2, then declares the one wire object to be using that pin, then declares the Dallas temperature sensor to be using that one wire object, opens a serial port, prints out some information, starts up the sensor, requests information from the sensor, and prints out the information and then waits. So let's hope this will work fine. I send it to the board. It is compiling, and once it's done, I will just open the serial port monitor and we'll check out what comes out from it. Okay, it's done uploading. Open the monitor, and you see here it says the temperature is being read pretty fast actually. I guess if we have more sensors we will see some sort of lag. I will change the camera just to show you that I'm heating it up, and I go back and you see how its temperature is going up. And the big difference with this one is that there is not that strange oscillation that we were getting from the LM35. It's a lot better reading, and you know, as a matter of fact, the prices for both sensors are quite similar. So, so if you need to make something where you need to have multiple temperature sensors, you can use this one. It's not so straightforward, so from a pedagogical point of view, it's a bit more complicated to explain. But you could use the same method I'm using to explain things as I'm using in this video, going from things that just work, that you can see directly how they work, but they are not so precise, to things that are a lot more precise and can give you a lot of meaningful information. So I have 2 more sensors to go. One of them I suspect is going to be super easy, which is this one, because I suspect this is a DS-B20 packaged in a waterproof container. I didn't bring any liquids today, not unlike the previous LiveCast, but it comes with 3 wires. I'm just gonna substitute the sensor I have there with this one. I suspect that red is gonna be power, black is gonna be ground, and white is gonna be signal. I keep my fingers crossed. So I will just make a quick substitution on the board, and I unplug the board. Take out the sensor. I keep it here. You know, when you have this kind of components that are so tiny that it's really hard, there is printed information on them, but it's so hard to read, it's a good idea to just keep them in the original packaging so people know where you found them. So I will just plug things in. On the one side is ground, on the other side. The tips of the component are not that, of the cable, sorry, they're not that peeled. So then there is signal here, and then there is power in the last one. There you go. So I'll just plug it in, and if everything works fine, I'm going to keep my hand here just to make sure that the signal is being captured properly. I open the serial port monitor, and you see it's measuring the temperature, and I heat it up. There you go. So it works. Super nice. So now I have a really good sensor to measure the cold temperature in the Baltic Sea. So yeah, insane. Okay, so let me just plug this out and turn off the serial port monitor here. And so now we saw 3 different types of sensors. Actually, the last one counts as the previous one because it's the exact same sensor, but just coming in a sealed, very practical package. I got no datasheet for it, so I have no idea whether this thing can work in like you know, super high temperatures like boiling water. So whether you could use this sensor to detect boiling water, I have no idea. So I should probably look for more information about that. Okay, Marcos comes from Switzerland. Hey, Marcos. So people are connecting slowly to the chat. So anybody connecting, feel free to say where you come from and give us some background information about yourself. It's good that we get to know each other. So I'm gonna go for the last sensor that I have for today. It's almost 8, so I said I didn't want to run for too long. And this is the classic Dht11, which is massively used humidity and temperature sensor. You will have seen it in a lot of projects because it comes integrated with everything and is kind of small. Comes with a plastic housing and you can put it outdoors, and that's kind of good. So I definitely need to remember to bring a scissor next time. So here we go. So this is how the sensor looks like. Okay. So these are packaged by a lot of different manufacturers these days. This one in particular, I have no idea what has inside, but we can look for information like we did before. So this is the Dht11, and as you can see in the images, well, actually the first image that shows up is how to hook up to Arduino. But you see it has 4 pins. One is power, one is ground, one is not used, and one is data. So this means that this is a digital temperature and humidity sensor that we're gonna need to use some sort of library to read the data from it. This is very important. So here we can see how it's hooked up, but we need some more information on how to read the data that is in it. So let's take a look at a full search on the internet, and well, we have information from our friend Adafruit, both in the website, which is their store, but also here on their documentation site. So let's take a look at the PDF from Adafruit. So yeah, let me make it bigger as usual. And this is a different packaging. The one that I have in my hand has taken the sensor itself and soldered it to a circuit board, so it's a bit more robust mechanically. And then you can plug it like this on a breadboard, because the pins of the sensor, they are really, really thin and they tend to break. So in this way, it's a lot more usable for classes. Also, you will see that it has only 3 pins, so they have taken out the non-usable pin. But now I'm live, and this is one of the inconveniences of being at the Arduino office. The alarm went off, so I'll come back in a second. It happens every week. I'm back. So welcome to the Arduino Live. We also have alarm systems. Okay, so there's the sensor, and as I said, the difference is that this one in the image has 4 pins, which one of them is not used, and that's what's been done here. So if you take a look at the circuit, you will see that the non-used pin is actually hooked up as non-used. And so the question is, okay, since one pin is not used, which one is the one that is hooked up? If you take a look at this particular one, if you take a look at the back of the circuit, it's going to be really hard to see, but I'm going to draw this for you. But the cables are very clearly connected in this way. So the first wire goes to the first one, the second one is like this, and then to this one, and then this one goes to here. And this is from the B side, okay? Looking at it from the back. So if you look at the pinout of the sensor that we saw earlier, probably it's down here in the PDF from Adafruit. Here, you see? It's telling you, okay, so it's actually the one on the left is on the left hand side is power. So if I'm looking at this sensor, when I'm looking at it, I'm looking at it from the back. So the left hand side is the right hand side. So this one is power. The one on the other side is ground. Okay, so this side is ground. The one that is hanging in the center is not used, but in my case, I have it connected to the one that is at the other side. Oh, it looks like, yeah, ground, power. So this one is signal. But somehow it is not making any sense. Oh yeah, ground. Okay, no, forget about what I just said. I was looking at it all wrong. So this thing I was telling you is wrong. So if anybody was following this and was hooking up this sensor, please unhook it. So if we look at it, I'm gonna do it differently. I'm gonna look at it from the front, this way. And it only has 3 pins out. So the way this is connected from the 4 pins that it has is like this: 1, 2, and 3. But this one through the back is connected to this one. So if this one here is power, this one here is power. Then if the one on the right is ground, this one is actually ground. And this one here is signal. Okay, so if you have got one of these with 3 pins, like this one, you have to make this mapping in the right way so you don't get into any kind of accidents and break your sensor. So I will then go back to my breadboard. Here I have the breadboard, hook up the sensor. And as I said, looking at it from the front, the one on the right hand side is ground. So I will take my black cable and I plug my black cable. And then the signal is the one in the center, the one in the center. And then the power is the one, no, sorry, the signal is the one on the left and the power is the one in the center. So this is a completely different pinout from the previous ones. So this is typically the place where people make mistakes and they get things burned. So you have to double check things at all times and make sure that you plug things. As I said, I had never plugged this sensor in my life before. I took it out from the package for the first time when I started this LiveCast. And if you're not careful, you might make a mistake. That's why I always buy 2. So the other thing is that you need to have a pull-up resistor. So I'm going to take the same pull-up resistor I had before between 5 volts and the data pin. There you go. And now I plug this to Arduino. So signal, according to this example, is plugged to pin number 2. Pin number 2. Power to pin number 5 volts and ground. There you go. So, okay, Rohit, don't don't worry, the YouTube transmission is going to be there for you to use later on. So the transmission is live, but everything stays recorded on Arduino's Arduino team YouTube channel. So don't worry, you can follow it. This is for the comment that we just got down here. So let's say, don't worry. It's being recorded. So as soon as we are done with the transmission, the program will have everything live. So now the question is, how do we program it? And again, as you see here, Adafruit recommends you to use their library for this. So we're going to just check on the library manager whether there is a Dht11 library. Probably there will be more than one, I suspect. So this basically is a digital sensor that that can read, that has two different sensors in the same package. So this is something that you will realize as you go. More and more sensors don't exist in isolation. They always exist with something else. For example, accelerometers, they typically have an internal temperature sensor because the temperature is used to calibrate the accelerometer so you get the right information. So this is very relevant because more and more sensors are going to be having this kind of like mixed interfaces. So we're going to get this library from Adafruit and install it, and then just run one example, and with that we'll have seen the last sensor of the day. So let's go to File, Examples, and here we see DHT sensor library, DHT unified sensor. Okay, here we go. So here's the DHT unified sensor. It is using the Adafruit sensor basic library, DHT. There you go. This means that we need to install the Adafruit unified sensor library because this example requires it and we don't have it. So we need to go to Sketch, Include Library, Manage Library, and we search for the word unified, Adafruit, Adafruit unified sensor. Here it is. There you go. So now we have both libraries that are needed for the example to work, the Adafruit unified library and the DHT sensor library. So then we see the sensor has to be connected to pin number 2. We define the type of sensor. The type of sensor is the Dht11. So if you are new to this, a lot of the things I'm doing right now might take you by surprise. Many of these libraries, they can be used for multiple devices, and especially Adafruit, they make libraries that can be used for tens or sometimes even hundreds of different screens, sensors, etc. So that with the same code, you can address a lot of different things, and then you have to be realizing slowly that you need to reconfigure variables and constants and so on to address the right part of the library. So in this case, we need to make sure that we activate that the DHT type sensor is the Dht11, which is the one we have, and not any of the other two available in this list. So when the library starts by instantiating an object from the DHT unified class, it says that it's gonna take the pin number 2, and it's saying there's a Dht11 kind of library, opens a serial port. It prints a lot of stuff because it's going to print a lot of information about which company made the sensor and so on and so forth, and then it will print the temperature and the humidity. And in the loop, it will be keeping a delay and keep on printing more information about both temperature and humidity at the same time. So it's quite a lot of information. And I don't see anywhere where delay MS is being declared with a value. I might be wrong. Here, yeah. So it's using the delay that is needed by the sensor readings. Okay, the sensor will have a certain amount of time that is needed to make a reading, and we'll use that information in order not to overlast the readings from the sensor. Okay, good. So we can then just send this down to the board, and then we will see all of the readings that we get from this sensor. There is a digital sensor, and this is a super inexpensive sensor used by a lot of people for many projects. And well, since it's digital, it's typically a bit harder to address. But here you go. So it's telling us the humidity has a certain value and the temperature is 23 degrees, humidity 6%. So I'm gonna just heat it up with my breath. Here you go. And you see how the humidity increased as well as the temperature, and how it slowly, keeps on increasing because of the reaction time of the sensor. So now, as long as there is air around the sensor, it's gonna keep the humidity high. So I'm gonna just try to put some air on it. As you see, by just blowing some air, the humidity is decreasing slowly and is now down to 20% again. Okay? So we basically saw today a series of different, first we saw a funny thing that was you can dip an Arduino board in the seawater and it still works. But then we're looking at temperature sensors. And the temperature sensors we saw were first a purely resistive sensor. And this requires to making a resistor divider between the sensor and the resistance. We used a pull down and we used 10K, and that gave us a nice range. But I insist this might vary from case to case. And then we use the LM35. There's a silicon sensor coming like this, which is an analog sensor. Here it says resistive, is just the behavior, but we read it through the analog pin. Okay, and it gives the temperature in Celsius degrees, which is very important, and it needs a pull-up resistor that we use 10K, and we saw that it oscillates, so it's not ideal, but it's very cheap and easy to use. So for projects with kids, can be convenient. Then we saw another silicon chip, but this time digital, and this was the DS18B20, which is a one-wire chip, which means you can use hundreds of them connected on a single data cable, and it gives information in degrees centigrades, and it's also using a pull-up, and it's quite precise and cheap. We saw a variation of this one that came coated in plastic. It's the same sensor, but it can be used in water or in other liquids. Okay, and finally we saw one that comes with this square package that has 4 pins. This is a Dht11, and it's also a digital sensor and measures temperature plus humidity. And as Billy mentioned right now in the chat, and I will just show you the chat to just have I like when people give opinions, so I'm actually really happy to bring it in. As Billy mentioned in the chat, it's very slow, up to 2 seconds to give a reading. Okay, so this is a summary of today's LiveCast. These are things we learned. So if you're thinking about making projects where you're using sensor technology, in particular temperature sensors, these are different options here I outlined for you, and you will need to think about the circumstances, what is that you want to measure, how much you control the place, how much money you can spend. Actually, money is less and less relevant when it comes to measure things that are so common as temperature, but it's most of the times about how complex your program can become. So people, this was it. It was a bit longer than an hour program. We had our classic issues of the day, like alarm sounding, David forgot his scissors, and so on. But it was a lot of fun. I kind of like it, and I invite you to please let me know through the chat now when I turn off the connection whether you like this kind of program that is a lot more hands-on, better than others we've done where we tell more prepared stories. And we will adjust according to whatever you guys think is better or best, sorry. So thank you very much, and see you on the internet next week.